Okay. All right. So with that, I think we'll spend the last 12 or so minutes talking through 1D steady state conduction. This is our first exploration into mathematical models. A lot of this is recap from 364 if you've had that. But again, useful recap. Hopefully you've done this kind of thing before, but we'll go through it. Okay, so 1D steady state conduction. What do we first of all mean? There's all these qualifiers. We've got conduction, we've got 1D steady state. Right, so what do these things mean? Well, if we have a problem like this, let's say, just use my laser. So if I pick a temperature here, right, there's a coordinate r theta, and z, right? All those three coordinates describe the position at which that temperature exists. If I have a spatial variation, let's say in the z direction, or the r direction, or even in the circumferential direction, right? I've got some temperature profile that's like this. It would be T, r, theta, z, right? So that is quite obviously a three-dimensional problem. Okay. We also care about the time component in heat transfer. So the most generalized model you could have would be temperature as a function of space and three coordinates and time, right? When we're talking about 1D steady state, what we mean is we're going to pick one dimension, right? One spatial dimension, and work with it. So we're talking about t as a function of r, or t as a function of x, or so on, right? So that's really what we mean 1D. In terms of steady state, it just means that there is no internal energy change component in our analysis. We're talking about heat flowing in a domain. The problem is not changing as a function of time. Okay. So we'll first, in our kind of first couple lectures, we're going to talk through 1D steady state and work through some problems there. These problems, you can solve them. 1D steady state, you can almost always solve them analytically or numerically. Right? So analytically would be, we do a control volume analysis, we come to energy balance, and then do differential equations, solve the differential equation, have an expression, analytical expression for temperature, right? That's our model. You can also do a numerical solution. Numerical solution is you discretize the domain up into a bunch of little nodes, and you represent each node with a set of algebraic equations. Right? We're going to do both of those things. For now, we're going to start with analytical. Okay. So the steps, right? The steps for analytical. So step one, we're going to define a differential control volume CV. Differential control volume. Okay, a couple things. First, let's do that. So differential control volume, I'm going to draw that over here. So I'm going to pick some rectangle. I'm drawing it like this. So why did I have my rectangle extend from the bottom to the top as opposed to the left wall to the right wall? Well, think about the differential control volume. What we're trying to do is come up with an expression for temperature as a function of a spatial coordinate, right? And if we need a temperature as a function of space, say r in this case, then everything in not r had better be uniform. Okay, so I can draw this control volume going from the bottom to the top because it's uniform in all directions, not r. Okay, so when we draw a differential control volume, we're talking about a differential that has a differential width in the direction that we want to model the temperature gradient. Okay, so what's going on here? Well, at this control volume, we're going to have, let me just zoom in a little bit. So we're going to have heat flow coming into this control volume. We'll call that Q dot at R. Okay, let's say this position here is R. Right, leaving the control volume, we've got heat flow again. We'll call that Q dot at R plus dr. And this width here is dr. The width of the differential element is dr. And do we have anything else going on? Okay, we could have, theoretically, you could have generation, or you could have energy conversion into heat within the control volume. In this problem, we don't have that. You could have a rate of change. So du, dt, we've said this is steady state. So in steady state problems, we don't have that either. So really all we have in this problem, by the way, these hatch marks here are meant to be indicating adiabatic, right? There's no heat transfer across that boundary. So the only thing we have is heat flow in at the R position and heat flow out at R plus dr. Okay, so it's a really simple problem. So we've defined our differential control volume. Okay, step two would be do the first law of thermodynamics. Basically do an energy balance. So what's our energy balance? Well, we would have anything coming in to our control volume, anything generated within the control volume must equal anything that's going out plus anything that's stored. Right? That's our energy balance, and like it's a lot simpler than thermal, right? Like you take thermal, you spend a lot of time on the energy balance. For heat transfer, it's usually very straightforward. Okay. As I said again, we don't have generation, we don't have storage, so we just have in equals out. So for this problem, what we're saying is heat flow at R must equal the heat flow at R plus dr. There is no change in heat flow. Right? Again, makes sense. Like where would it go? We have adiabatic boundaries, we don't have generation or storage. What's going in must be what's going out. Okay. Step three, take the limit as dr approaches 0. So now we're taking our control volume and making, we've drawn it with a finite size, we're making it differentially small, taking the limit as dr goes to 0. Okay, what does that get us? Well, let's remember the definition of the derivative. So let's say dq dot r, dr is the limit as dr goes to 0. Of the definition of the derivative gives us q dot r plus dr minus q dot r over dr. Right? This is just a definition. Okay, so we want to use this definition to give us some indication of what's happening on the right-hand side of that equation on top. Right? Q dot r plus dr is not really a useful thing other than just a name for what's happening. So we need to solve for an equation that tells us what's happening at r plus dr. So let's just rearrange this equation a little bit to solve for q dot r plus dr. Okay, so we end up with q dot r plus dr equals q dot r plus dq dot r dr times dr. Just rearranging that equation. Okay, so now we can take this guy here, and we're going to substitute that into the equation up here, right? Our energy balance equation, right? And we end up with this equation, q dot r is equal to q dot r plus dq dot r dr times dr. Okay, now we can do some simplification. This goes away, same thing, left and right. We're left with this over here has to be equal to 0. Okay, if this is equal to 0, we have this differential width here, right? We can actually divide that out, all right? So we end up with dq dot r dr equals 0. Again, this makes sense, right? This is intuitive. We're saying the rate of change of heat transfer with respect to the coordinate r is 0. There's no place that heat's going other than in versus out, so it doesn't change. dq dot r dr is 0 for this problem. Okay, step 4, substitute this into the rate equation. So substituting, so what is our rate equation here? What is our rate equation, by the way? So our rate equation is a way of relating heat transfer to temperature. And if we want to be able to calculate heat transfer and relate that to temperature, we need an equation that does that for whichever mode of heat transfer we're using. So for conduction, our rate equation is Fourier's law, right? So that is, for this, it would be q dot r is equal to minus k times dt, partial t dr. Okay, notice we have written this in terms of heat flux, q dot double prime. We need to actually get this into q dot, right? Because our energy balance is in terms of q dot, not q dot double prime. So we need to multiply by the area. Okay, so that gives us Q dot R is equal to, like, what's the area of the differential element? Okay, well, that's going to be minus K times 2 pi R. That's the kind of the circumference at the control volume's position, 2 pi R, times, I think it was L. Let's see. Yeah, right. So this coordinate here is L. So ultimately, we're trying to find, right, what is this area of this cylinder, right? Okay, so 2 pi R L, and then multiplied by dt dr. Right? This now becomes an ordinary differential equation because it's only a function of R. Okay, let's see, moving through this, there's a couple of minutes left, 1 minute left. So I'll just kind of go through this quickly. I think you've seen it before. So let's substitute this back in, or this substitutes back into this equation over here. So we end up with d dr minus k times 2 pi r L dt dr equals 0. Okay, minus k, 2 pi, and L, those all cancel out. Okay, and we're left with this equation, d dr. R does not cancel out, R is still there, dt dr equals 0. All right, and then our task is just to solve this differential equation to come to a solution in temperature. All right, so we can solve this pretty easily, right? The variables can be separated, so we don't have any issue there. So first we're gonna bring this over to the other side, and we're gonna say dr dt dr equals 0, dr. We're gonna integrate both sides. We end up with r dt dr equals 0. Integral of 0 with respect to r is just a constant. Okay, we can integrate this again, and we end up with the solution t is equal to c1 times the log of r plus c2. Okay, so that's where we end up. So next time what we're going to do is talk through boundary conditions, right? How you identify and enforce those boundary conditions. All right. Thanks, everyone.